This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, Passive Intermodulation Concerns in In-Building Wireless Systems, presented by Anritsu. Our presenter today is Tom Bell, Senior Product Manager at Anritsu. It's always great to have Tom back on a webinar. At this time, I'd like to pass the presentation over to Tom.
All right, thanks, Kyle. So jumping right into it, the agenda for this is to start off with a review of what is passive intermodulation. I always have way too many slides on this, so I'm going to try to go through that relatively quickly. It'll be there that you can review later if you download the presentation or look at the review of the webinar. Then talk about in-building wireless architectures, and then speak about how PIM, the level of PIM concern changes based on the architecture you're dealing with. And then at the end, talk a little bit about ways to mitigate PIM, especially external PIM that can occur around antennas. I do want to plug the white paper, which is shown to the right here, this Understanding In-Building Wireless Solutions. It's a much more in-depth summary of the architectures used for in-building wireless systems. You can access that from the simplest way is actually to go to Google and Google the name Understanding In-Building Wireless, and I think the link to where you can download it from the RCR website is the first link that appears. So what is PIM? Well, PIM is interference. It's new frequencies that are generated by the transmit signals or downlink signals at a website or at a cell site when they interact with nonlinear junctions or nonlinear materials in the RF path. And these new frequencies that are generated, if they fall in the uplink band of the system, they can cause interference, causing the noise floor to rise, causing dropped calls, access failures, slower data rates. When I talk about nonlinear, I'm talking about the relationship between current and voltage, specifically at metal-to-metal contacts throughout the RF path. So if I have a high-pressure metal-to-metal contact or one that is welded or soldered where the surfaces are not separating, as the voltage increases, I get a linear increase in current. On the contrast, if I have a non-linear junction, one that the metal-to-metal contact is very loose or has oxide layers or small gaps where I might get micro-arcing across the gap, as the voltage increases, I do not get a direct current increase. Then all of a sudden I get a rapid increase. And that schematically looks a lot like a diode. So these nonlinear junctions are acting like microscopic diodes distributed throughout the passive RF path. Well, what can be nonlinear in an in-building wireless system? Well, this problem, passive intermodulation, is a concern in the RF sections. So if I have poor cable terminations where I have metal flakes that were caused by the cutting process, or if I have damaged components in the system, or even things like high-powered RF terminations. By design, these can cause passive intermodulation. Loose connections, type N connections are typically poor for PIM. It's not that there's anything necessarily wrong with the type N interface. It's just that the range of acceptable torques is very narrow, that if I over-torque it, I break the contacts and I cause PIM. If I under-torque it, it becomes loose and it causes PIM. So type N is not a highly desired connector type for in-building wireless systems. If I have metal flakes inside the connectors, these metal flakes can be sources of passive intermodulation. And then finally, if I have loose metal objects near antennas, those can all be sources of PIM. And if you look at this picture at the lower left, you know, this is just a typical in-building wireless antenna location, and you can just count how many things around this antenna are potentially loose metal objects. So the in-building environment is target rich when it comes to passive intermodulation. We know what the frequencies are that will be generated by the downlink signals. Passive intermodulation is a mathematical combination of the frequencies you're starting with. And you can see here on this slide, I defined the mathematics for calculating where the frequencies will occur for the odd intermodulation products. We spend a lot of time talking about the odd products because they occur physically close to the transmit signals that are generating them. And so it's more likely that the downlink signals from a given band will impact the odd products are more likely to fall in the uplink band for that system. If you look at this example, this is a frequency combination that's common in the Asia Pacific region, where the 850 megahertz transmit or downlink is adjacent to the 900 megahertz uplink. And here, the third order and fifth order and seventh order are falling in the 900 megahertz uplink, whereas it's only the ninth order product that falls in the 850 zone receive band. So this is a classic problem of when I put these frequencies together, I'm getting low order intermodulation products falling in the band, which we'll see later in the presentation has a big impact on the amount of noise that's generated. But in building systems, we're combining frequencies that are very far apart, separated in frequency, and so we also now have to be concerned about the even products. And so this is showing for a 900 megahertz system, for example, the fact that the IM4 and IM6 are able to fall in the 2100 megahertz uplink band. The magnitude of the PIM, as I said before, the lower the intermodulation order, the higher the magnitude. So as an example, if we have a system that's nonlinear and the IM3 is some level, the fifth order product is typically 20 dB lower than that. And each additional product above that becomes an additional 15 dB lower. Now, no two PIM sources are exactly the same, and the numbers I'm showing here are based on thousands of measurements and coming up with an average of what it tends to look like. But the message here is, if you notice, the magnitude difference between IM3 and IM9 in this case is 50 dB. So if I have IM3 falling in my band, the signal is typically 50 dB higher than if it's IM9 that's falling in my band. So looking at some typical applications, and I'm just in this particular presentation, I'm choosing the European frequency bands and saying what low order products, and specifically I mean IM2, IM3, IM4, and IM5, which combinations can cause those low order products to fall in any one of the receive bands. And so starting with the lower frequencies, the ones less than 1 gigahertz, you can see that the bands themselves are typically causing IM3s and IM5s to fall in their own receive band. However, when I take into account all the other frequencies that potentially could be in that system, you get all of these other potential combinations. So the message here is that the more frequencies I have together in a system, the higher the probability that one of these low order products, the high magnitude products, is going to fall into one or more of the operator's receive bands that are present. If we carry this further to look at the bands above 1 gigahertz, we have the same scenario, that the 1800 megahertz can cause IM3 and IM5 on itself, as well as onto the 2100 megahertz uplink, whereas because of the large duplex spacing between the 2100 megahertz downlink and uplink, it's only IM7 that it can generate on itself. But when we take into account all the other frequency bands, we get IM2s, a large number of IM4s, IM3s, IM5s. So once again, all of these other frequencies are playing together in these in-building systems to cause interference on all the other bands that are present. And carrying that to the last step, which is the 2.6 gigahertz band, once again, if it's TDD or FDD transmits, those can cause IM3 or IM5 into the FDD receive. And once again, combinations of the lower frequencies can all generate low intermodulation products that impact the 2.6 gigahertz receive. So far we've been talking about PIM as individual frequencies. We need to know that the bandwidth of the IM is proportional to the bandwidth of the signals you're starting with, and is proportional to the intermodulation product order. So if I have two 200 kilohertz signals that are mixing, the third order intermodulation product is going to be 3 times the bandwidth of that individual signal. IM5 is 5 times, 7 is 7 times, 9 is 9 times, etc. When I look at LTE, LTE is made up of many subcarriers that are all firing individually. And so what you end up with this case is what I call the wedding cake of PIM that forms around the LTE carrier itself. So if I have a 10 megahertz wide LTE carrier, the bandwidth of IM3 is 30 megahertz wide. and IM5 is 50 megahertz wide. So instead of seeing individual spikes occurring in my uplink band, I'm just seeing a general noise rise. And in the case of LTE, the magnitude of the noise is increasing as I get closer to the carrier that's causing it. So instead of it being a straight line of interference, it ends up looking like a sloping line of interference caused by that LTE carrier. Now, once again, if I'm concerned about the odd product wedding cake, I also have the even product wedding cake that is also out there causing problems with LTE systems. And this is the classic Sharkfin view that you would see if you attached a spectrum analyzer to the receive monitor port of a base station and looked at this sloping increase in PIM in frequency within the operating band of that system. It looks like a straight line, but since the receive filtering of the base station cuts off frequencies above 716 and below 698 in this case, you see the cutoff of the filter, you now see the noise rise, and then you see the cutoff on the other side. So if you are using a spectrum analyzer and looking at noise rise in a receive band, and you see this shark fin looking response, it's a good indication that passive intermodulation is the source of that noise rise, and you can determine which carrier is causing it because the increase in noise is pointing in the direction of the carrier that's causing that PIM. I get asked all the time, what about TDD or time division duplex systems? Is PIM a problem in a TDD system? Well, a TDD system by itself is not impacted by PIM. And the reason is that when you're transmitting and when the PIM is being generated, you're not receiving. And so therefore I'm generating PIM, I have a guard period, and then I start to receive. So PIM generated by my own transmit signals are not causing interference into my own receive band in a TDD system. However, TDD will certainly create IM products around itself, and so if that TDD system is adjacent to another TDD system or adjacent to the receive band of an FDD system, it still can spill over and cause PIM interference into the adjacent bands. And looking at this case, this is a case where we put an LTE transmit signal within 1 megahertz of a receive band, and you can see here, in this particular nonlinearity that we had, we were able to easily achieve 20 to 25 dB of noise increase caused by that adjacent carrier. So one of the messages here is if you are doing TDD and you have many frequency bands adjacent to each other, you either need to add frequency separation between the bands to account for this intermodulation, or you're going to need to synchronize the transmits between the adjacent bands so that you're not having one band transmitting while the adjacent band is receiving. So what do we do to reduce the PIM interference? Well, it's pretty simple. The problem is caused by these nonlinearities, so we need to make them more linear. And it's relatively simple, actually. To make things more linear, it's things like taking loose connectors and making them tight, and taking metal flakes that are in the system and getting rid of them. Braided cables, replacing them with solid conductor cables. And if it's PIM near an antenna, try either relocating the PIM or relocating the antenna. And how do we measure linearity? Well, we use a PIM tester. A PIM tester is a specific instrument designed to test linearity. And we do that by transmitting two known frequencies into the system, and we transmit those frequencies and hope we never see them coming back, because the instrument is designed to measure the noise that's created by those signals as they pass through the system. If there is a PIM source, either in the feed system or beyond the feed system, when the transmit frequencies of our test instruments pass through it, PIM is generated. It acts like a point source radiator, meaning that the PIM signal will follow the transmit signals out as well as go back towards the receiver. And so our PIM test instrument is designed to transmit the high-power test signals and receive at the third order intermodulation product frequency. The instrument can be set to measure third, fifth, or seventh, but typically IM3 is used as it characterizes the linearity of the system. meaning that if IM3 is low, the linearity of the system is good, and if IM3 is high, the linearity of the system is poor. So now talking about in-building wireless systems, what impacts the severity of PIM in an in-building system? Well, first and foremost, which IM products are falling in band is going to have the largest impact. So that if I have IM2s and IM3s falling in band, the problem is much, much higher than if it's IM9s and IM7s. Also, back to that original slide where I was talking about the multiple frequency combinations, the more bands present in the system increases the probability that one of those low order products is going to fall in band. The next thing that impacts it is the degree of nonlinearity of the PIM source. And unfortunately for in-building systems, we're putting antennas in areas that have extremely nonlinear objects. It's much, much worse than a typical outdoor environment where you're just not radiating significant number of metal objects around the antenna. You're typically trying to put the antenna in a location where it has a clear view of the sector it's serving. Well, indoors, by definition, you are spraying energy everywhere, and you're exciting extremely nonlinear objects. And then finally, the amount of current flowing through the nonlinear junction is going to impact how high the magnitude of PIM is that's generated. So higher current equals higher PIM. Obviously, if the power level, if I'm transmitting 43 dBm compared to 30 dBm, the higher power that I'm transmitting is going to cause higher current. So that's kind of obvious. What may be less obvious is that not the current density throughout that transmission line and throughout components in the system is not the same at all locations. So you may have a nonlinearity that just happens to be in a location that's not being excited. With the case of external PIM, we'll show in some data later on that the location of that PIM source relative to the antenna makes a big difference in how much PIM is actually being generated by that system. Okay, so before we start talking about in-building systems, it's important to make sure we have a common definitions of how to describe the different architectures that are available out there for deploying these systems. I started working on a paper, gosh, I want to say months ago, and it started off being called Understanding Distributed Antenna Systems. And I kept finding examples of these different configurations that weren't exactly a DAS. And so I kept struggling and finally found this definition of breaking it up into distributed antenna systems, distributed radio systems, and distributed small cells. And it seems to make sense. If you look at any given system out there, with a little bit of logic, you can decide what type of system you're looking at. And the main differentiator between these is where are the network equipment manufacturers' baseband processing and radio functions. So if it's a distributed antenna system, the radio functions and the baseband processing from the network equipment manufacturer are centralized. And those signals are then distributed to antennas that are within the venue. Now, the method of distribution can be passive RF, it could be active systems, it could be a combination of passive or active, it could be analog, it could be digital, it doesn't matter. As long as the network equipment manufacturers' baseband processing radio functions are centralized, that by definition is a DAS. The next type is a distributed radio system, and in this case, the baseband processing is centralized. However, the network equipment manufacturer's radio functions are distributed along with the antennas. In this case, we have a front haul link between the baseband processing and the radio. Typical examples of this type of a system might be the Ericsson DOT or the Huawei LampSite solution. And then finally, distributed small cells. In this case, the baseband processing, the radio, and the antenna are all distributed throughout the system. The small cell is a micro base station, and so in this case, we have only backhaul that we're dealing with from the individual base stations to a centralized coordination point back into the core network. So now we'll finally get to the point of talking about PIM concerns in the different locations within each of these architectures. So in the next several slides, I'm going to be showing a generic architecture for each of the different systems I described before. And in each one of the systems, there will be some number of signal sources combined together and feeding 2 floors of this fictitious building. In this case, it's a passive DAS, meaning I have centralized baseband processing and centralized radio resources that are coming together through a combining system, all in RF, feeding into a distribution system which feeds the energy out to individual antennas distributed throughout the system. In this case, in a passive DAS, there is only losses from the output of the signal source all the way to the antenna. There's no active components here. From a PIM perspective, we can describe the severity of the PIM in this color bar that I have to the right. So if the PIM is severe in that particular location, I've colored it red. If there's little or no PIM concern, it becomes white. And if it's somewhere in between, it's going to be orange if it's closer to severe, and it's yellow if it's closer to less severe. So that's my PIM severity scale. So going back to the passive DAS system, these signal sources are generally transmitting at high RF power, but they also are single frequency bands. So in this segment of the DAS, we have the highest RF power we're going to experience, which we know is increasing PIM, but it's probably IM7 or IM9 that actually is going to impact that individual signal source's receiver. So it's not the most severe, but it is severe. It's at an orange level of concern for the system. Once I go past the combiner, and I've combined, in this case, the red, the blue, and the orange signal sources together, because I've increased the probability of a low-order product, the PIM severity is now red or high. I'm at the highest power I'm going to be in the system, or a very high level of power in the system, and I have multiple frequencies that are probably causing a low-order product. So beyond the first level of combination in the system is where we have the most severe concerns for PIM in a passive DAS. By the time I get out to the floor levels, I'm typically down to 30 dBm or approximately 1 watt. Here, the power is lower, which is reducing the severity, but I still have all these different frequencies together, meaning I probably have low-order products. So we're at a medium level of concern at the floor level. When I get to the antenna, I'm now down typically on the order of 20 dBm or 100 milliwatts. The power level is much lower, but I still have all these different frequencies, high probability of low-order product, and I'm now in an area that, as we said before, is very target-rich when it comes to high nonlinear objects. So beyond the antenna in a passive DAS, a multi-operator neutral host system, we still have a level of concern for PIM at and beyond the antenna. If we carry the same analysis to an active DAS, looking at the signal sources, I have the exact same concern from feeding the RF signal source into the point of interface. So here I still have the orange level of concern. It's a high power, but it's probably IM7 or IM9 that's actually falling in band. The point of interface tray typically has 2 functions. One is to separate the transmit and receive signals, and secondly, to attenuate the transmit signal down to approximately 0 dBm before it feeds into the optical equipment at the head end of the DAS. So at the output of this point of interface tray, PIM is not a concern. And the reason I say that is that we've separated transmit and receive, and there's typically an isolation of approximately 60 dB between transmit and receive, which means that even if I did generate PIM in this section, it would be attenuated 60 dB or attenuated by the isolation of the duplexer before it could make it back into the receive path to get into that system. That, in combination with the fact that we're down at 0 dB in power, means that PIM is just not a concern in this section of a DAS. And that's why you'll see from most of the implementations, they're using braided cables with QMA or SMA connections. There's very little concern for PIM here because it's just not going to cause interference in the system. When I convert to the RF to optical and transport over the optical fibers, PIM is not a concern in the optical fibers. When I get out to the radio units, I'm converting back to RF, and at this point, I'm back to the same yellow level of concern. I have multiple frequencies in a very high PIM environment, and 100 milliwatts is still plenty of power to excite and cause PIM problems. The external PIM problems don't care how the RF energy got there, whether it was fed by a passive system or fed by an active system. It makes no difference. It has a certain level of power, multiple frequencies, and a nonlinearity. Hybrid DAS is a combination of active and passive, and it's pretty obvious if you just look at count the number of components between this hybrid system and this active system. This is done to save cost. We can cover the same area by deploying the radio units in equipment closets on a floor as opposed to at each individual location. It means I can worry about only putting the fiber running to one place, having power going to one place. It just ends up being a great simplification to the cost of the system, which is why we see lots of hybrid DAS systems deployed. So in the head-end equipment room, exact same as an active DAS, we still have an orange level of concern up to the point of interface, no concern after the point of interface in the RF section. Fiber's not a problem. When I get to the floor level, it's now the same level of concern as it was in a passive DAS. And then once again at the antenna level, same level of concern. I included a separate slide to talk about digital active DAS because it gives you an opportunity to think about some of the other ways that you can feed these systems. So in a digital DAS, instead of being over the fiber, instead of having an analog transfer of the RF signals that are fed in, we're now digitizing the information and sending it as a digital signal on the optical fiber. That also means that if I have a SIPRI input into this system, I can now transport that SIPRI over the digital interface out to the expansion units and ultimately out to the individual radios. So that's interesting because it lets you think about concepts like CRAN feeding in or only putting a BBU into the base station. I'm no longer dealing with the attenuation of all this power. Lots of good benefits that can come from this. From a configuration standpoint, I'm still calling it a DAS, and the reason being that I still have these scenarios where I'm feeding centrally located baseband processing and radio resources, even though in this case it's questionable where the radio resource is. Is it the network equipment manufacturers? Is it the DAS manufacturers? It's a little confusing, but because I can have multi-operator and because I can still have centralized functions, I'm calling this a digital DAS as opposed to the next one we'll talk about, which is the distributed radio system. So here once again, the RF signals from the signal sources in the point of interface were still an orange level of concern. The SIPRI interface into the radio head or the head-end equipment, no concern at all. Fiber is not a concern. The LAN cables used for distributing from the expansion units to the radio units, not a concern. But when we get to the antennas, we still have multiple frequencies. At 100 milliwatts, we still are at a yellow level of concern. So now looking at distributed radio systems. Distributed radio systems like the Ericsson DOT or the Huawei LampSite are typically single operator systems, which means that I generally don't have multiple frequencies being deployed at the antenna. So that case means that I'm probably, instead of an IM2 or an IM3, it's maybe IM7 or IM9 that's actually the IM product that can impact this receive band. And so for that case, in these scenarios, I would say that PIM is probably not a concern in a typical distributed radio system. However, if I start deploying multiband systems, and in particular if it's low-frequency multiband systems, which we'll talk more about later, I now creep back into the yellow level of concern. So the great thing about this architecture is I've eliminated all of the concerns up to the point of getting to the antenna, and now I've limited my concerns to being only those things around the antenna. Distributed small cells are the same. The feed system, if you will, that's feeding all of those individual small cells, the Ethernet backhaul going through the controller back to the core network, we've eliminated all PIM concerns in this section of the in-building system. But we're now back to the antenna and things around the antenna. So if it's a single band distributed or distributed small cell system, PIM is probably not going to be a concern. As I add multiple bands, and even if I add multiple operators, as I've seen advertised by some small cell manufacturers, I'm now creeping back into the yellow level of concern. All right, so I've been talking a lot about 100 milliwatts being a problem in building, and I can almost feel the people on the call saying, well, that's crazy. There's no way that 100 milliwatts is going to be able to generate enough PIM to be an issue. And this is relatively complicated data to look at, but in general, what I've done here is took 4 different PIM analyzers at 700, 850, 1900, and 2600 megahertz, and fed their outputs together into a single cable feeding a single antenna. And we took this antenna, we put it near the ceiling, and just walked across a 10-meter section of an office space to look at how do the different frequencies react to the random nonlinearities that you might find in this typical office environment. And what we did then is we drew this nice dotted line across the data that said, all right, this line is a level of minus 108 dBm, and in this particular case, if the loss of the system getting back to the receiver, we felt like that anything above minus 108 at this level could potentially impact system performance. And then put that same line on all of the different plots, and then looked at what was the probability of success. So in this case, looking at the 55%, it means that if we randomly installed an antenna somewhere along that 10-meter walk, we have a 55% chance of putting it in a location that didn't cause high enough PIM to impact system performance. And then additionally at 2600, same thing. In this case, at 2600, we could have put it anywhere. The PIM was it was just non-reactive at the 2600 megahertz system. As I go lower and lower in frequency, you can see that the probability becomes higher and higher or lower and lower that you're going to have a success. So another way of thinking about this is if I'm deploying an in-building system that has 1,000 antennas, if the system's being deployed at 2600 megahertz, I probably don't have to worry about any of those antennas. If it's at 700 megahertz, 450 of those antennas are probably going to be impacted by the environment that they're installed in. So once again, PIM is a concern at low powers, and in this case, it's only 32 milliwatts that's actually being transmitted at the antenna. So we're down at 15 dBm and still achieving PIM at a level that actually is saturating the receiver of the PIM analyzer. So what can I do to prevent PIM in in-building wireless systems? Well, first, avoid frequency combinations that generate low IM order products. If that's possible, that's the simplest and easiest way to combat passive intermodulation. The second is use low PIM construction techniques and use low PIM materials. And then finally, avoid putting antennas near nonlinear objects. Now, in a neutral host system that's deployed indoors, you probably don't have control over number 1 and number 3. So you need to look at what can I do to help mitigate these PIM problems. So specifically looking at this common thread of PIM beyond the antenna, what can I do to combat that? Well, one thing you can do is move the antenna. It turns out that the reason we were seeing such a more reactive response to PIM in the ceiling at the low frequency is that at lower the frequency, the larger the diameter of the near field region around that antenna. And as it turns out, as I get the PIM source into the near field, I'm now coupling directly energy into that PIM source as opposed to radiating to it. And so if I can take a PIM source and move it from a near field problem to a far field problem, I can dramatically reduce the magnitude of the PIM that's created. So this data is taken at 700 megahertz by taking a PIM source, which is a diode on the top of this post, and moving it closer or farther away from the antenna and measuring what the magnitude is, and we did this at multiple power levels. If I look at the blue line, this is 20 dBm, and it says that if I take that PIM problem from being a near field problem to a far field problem, I'm getting 60 dB reduction. So the simple thing to do here is if there's PIM at an antenna location, relocate the antenna. And it doesn't mean moving it to a different room. It means that all I have to do is typically move that antenna within 1 meter of its existing design location, and I can probably find a location that is down here in the taking my PIM problem into the far field instead of being into the near field. The other option is move the PIM source. So these pictures are both taken from a stadium DAS that I had the pleasure of walking through. And if you look at the one to the left, we have this nice new conduit that was added after the DAS was commissioned. And it turns out that all of the antennas along this zone have this nice new coax or conduit that was feeding the new fan system that's been added, which we believe is now causing passive intermodulation and causing a noise rise in this zone. So now that football season is over, a job will be commissioned to actually go and relocate this conduit to see if we can eliminate the PIM problems in that zone. Another thing that's interesting is in stadium applications, every antenna I've ever seen has these additional stainless steel safety chains so that if for some reason the antenna mounting structure were to break or corrode, the antenna couldn't fall off and hurt somebody in the stadium. Well, interestingly enough, this is loose metal-to-metal contact sitting directly next to an antenna, and it's definitely in the near field. So if you have things like this, you could do something simple like just wrap it in electrical tape to prevent the metal-to-metal surfaces from touching each other as a way to solve the PIM problem. Another option is to add attenuation between the antenna and the PIM source. Now, I've played with some very expensive materials from different anechoic chamber manufacturers that do a fine job of attenuating the signal. But some simple things can work too. In this case, I have a PIM source that's next to an antenna that's generating a very, very high level of PIM. If I do something simple just to block the energy from getting to that PIM source using, in this case, aluminum duct tape, I was able to make a more than 40 dB reduction. So if you can't move the antenna and you can't fix the PIM source, maybe the thing to do is to add attenuation. And then finally, this is one I find interesting. If another option is to reduce the amount of power that you're radiating at the PIM source. So in most antennas that you see, it's an omnidirectional antenna, meaning that the radiation from that antenna is going to be equal in all azimuth directions. In this particular case, this is an antenna supplied to me by JMA Wireless that has a notch in the pattern, meaning that in one direction of this antenna, the gain is intentionally reduced so that if you have a site where the antenna is installed and it's causing PIM, I can take that antenna out and replace it with this notch beam antenna and rotate the antenna until I steer the null in the pattern in the direction of the PIM source. And looking at the data here, I measured it at both a high frequency as well as a low frequency. It was very effective. You know, the different lines here are different physical distances of this diode relative to the antenna next to it, and you can see the magnitude as I steer that notch towards the PIM source. I'm getting as much as 30 dB reduction in the PIM. So that could be a very useful tool that you build your system out with Omni antennas. If you have a site that's got a bad location, swap out that antenna and see if by just rotating the antenna you can change your PIM levels. So now we're to the conclusion of the summary. So PIM severity is going to be different in every in-building wireless installation. The type of construction, as we've seen, has a big impact. The number of frequency bands and which frequency bands in use has an impact. The power levels of where you are in the system, as well as what the starting power is in the system, has an impact. PIM is and can be a problem at very low power levels. Once again, if I have low intermodulation products falling in the receive band at power levels greater than 20 dBm, I need to be concerned. And then finally, PIM can be mitigated by using one of the techniques that I showed at the end. You can either eliminate the bad frequency combinations to begin with, you can use low PIM construction materials, or just reduce the energy level arriving at that PIM source by one of the techniques described. And that's it. Kyle, I think we're ready for questions.
All right, thanks, Tom. We've had quite a few questions come in, but of course, everyone, please submit your questions if you have any. We'll try to get to them if we can. If not, I will send a copy of all questions to Tom. Okay, let's get started. So the first one, back on slide 9, you showed multi-band PIM combinations in Europe. What tool did you use to calculate those frequency combinations?
Yeah, I wish I had a really nice tool for doing that. I used the brute force method of creating a spreadsheet in Excel that allows me to look at two-tone combinations as well as looking at up to four-tone calculations. So it's got something like 1,000 lines of calculations, and it's an ugly process, but at least it allows me to do these types of analysis relatively quickly.
I guess sometimes the simplest method is the best. Anyways, you talked about public safety a bit. What about public safety frequency bands? Is PIM a problem in public safety DAS installations?
Yeah, it can be. Once again, you have to look at the specific frequencies that are in use. And I've seen scenarios where, if using the North American frequencies, if I only have the existing 800 megahertz systems and maybe the existing 900 megahertz systems together, I generally don't have a problem. It ends up being, I think, IM9 that is typically what's falling in band. As soon as I combine that with the commercial frequencies, I immediately start picking up IM3s. So the best scenario is if you can keep your public safety DAS separate from the commercial DAS, you just eliminate a lot of potential combinations. I guess I'm concerned about as FirstNet starts deploying the 700 megahertz spectrum, which now introduces the broadband 700 megahertz into the mix. I'm concerned there because I can see combinations that are creeping up. I get some natural IM5s, but once again, if that is combined with the commercial 700 megahertz, I definitely have IM3s to be concerned with.
Okay, thanks. We had a question about the material of connectors. What type of connector platings are PIM acceptable?
Each of the connector manufacturers has their own brand or trade name for the plating systems that they use. So in general, what you're trying to avoid in most cases is trying to avoid nickel. Nickel is a great material as an anti-diffusion layer that keeps the brass underneath from migrating through and wreaking havoc at the mating surfaces. But each of the different manufacturers has their own mix or brand of their version of the low PIM materials they're using. So the key is look for plating systems that do not include nickel, and in most cases after that, you're in good shape.
Okay, great. Next question. Is there a rule of thumb to identify key PIM test points during in-building DAS designs?
Points of test. Yeah, I think what I'd like to do is refer everyone to the IWPC. There's a white paper that the industry has gotten together and created that can be found there. It's www.iwpc.org. There's a white paper on their homepage that's free to download, which includes a PIM testing best practices document for field testing, and specifically there's an entire chapter in there that's focused on in-building wireless systems, and it describes a system of saying, it basically puts it out there that says you have two choices. You can test as you go, or you can build it all and then test it later and try to go backwards and find the problems. So the document is tried to be fair to say, look, both of them will work. It's just a question of how good you are at the assembly and how lucky you are on avoiding those 450 bad antennas. The most rigorous process says that you should first check the antenna locations using a low PIM antenna location test to begin with. So instead of installing the antenna and then figuring out you've got a problem, go to the location, perform a low power PIM test, determine if the location is good to begin with. And usually you can move the antenna around fairly easily at that point. And if you move it a meter away and find a clean location, install it there. So that's the antenna location test is usually the first test you would do. Then if you're using the build as you go method, you would then build branches together and test sub-branches to make sure that the branch is good. Take known branches, put them together to create floors, to create known good floors. Then take your riser, test it individually, make sure it's good, and then add on the floor. So it's a build as you go process. And every time a human is involved with connecting additional components, you've created the opportunity to cause PIM. So that's kind of the way to think about it, is you want to build it, make sure it's good, and build it into the next higher system.
Okay, Tom, what was that website again for to download that white paper?
Yeah, it's from the IWPC, so www.iwpc.org, O-R-G.
Cool, perfect. So the next question, it's does PIM affect a macro setup?
I'm sorry, say it again?
Does PIM affect a macro setup?
PIM affect the macro setup? I don't think so. The things that I think of in the setup of a macro are neighbor lists and how it's communicating and things like that. PIM is just something to be avoided. It's an interferer that you don't plan for it in the base station setup. You are think of it like an external interferer where someone's broadcasting at your frequency into your system. The solution is to go take care of the interference.
Okay, great. Next question. What are some examples of high power termination that can actually cause PIM?
Um, I kind of answer that the backwards way. A low PIM termination is typically one that's constructed as a cable load, which means that the termination is nothing but a long length of very small diameter coax that's wound around a spool to generate high insertion loss because of the small diameter of the coax. And so a low PIM termination takes the power and slowly dissipates it due to the insertion loss of the cable, and they're typically on the order of 20 dB of insertion loss at the lowest frequencies you'd be testing. If I look at other forms of RF terminations, they generally take some type of a carbon resistive element inside the box that you're transmitting in, and have a tapered resistive material that is designed to attenuate the signal into this resistive material in a very, very small space, relatively inexpensive, and do it in such a way that doesn't cause high reflection. Well, those carbon materials are notorious for having very high passive intermodulation, because you can think about it, the carbon particles are all millions of lightly touching metal-to-metal objects, if you will, and that's a terrible PIM source. So those carbon-based resistive terminations are to be avoided. Now, to be fair, if you looked at the orientation or the configuration for all of my signal sources, I show a high-powered termination at the hybrid combiner at the input of each of those signal sources. You need to be careful that just because the third-order intermodulation product of that high-power combiner is bad, it doesn't mean that it's not going to work in that particular system. So let's take the example of a 2100 megahertz system. If its IM7 is the lowest order product that can fall in band, that resistive termination may be perfectly fine in that particular application. But if you took that same resistive termination and put it after the combiner, where I have multiple frequency bands, now it's unacceptable.
Okay. Next questions kind of goes similar to that. So if a carrier owns multiple frequency bands, is there a best way to tell which frequency band should be used for PIM testing?
Yeah, actually, there's a whole nother webinar, and it's about to be published again as a white paper on that subject. So I would say probably if you want an exhaustive description of that, go check out the other webinars on that subject that I've done with Anritsu. The short answer is that because of this external PIM problem, it's most reactive the lower you go in frequency. My recommendation is always test at the lowest frequency you plan to use, but you also should test at least one high band frequency. And the reason being that we found that the loose metal-metal contact, or the loose connector type of PIM, seems to be much more reactive at the high frequencies, whereas the external PIM seems to be much more reactive at the low frequencies.
Okay, great. Next question we had for PIM beyond the antenna. How do you figure out which metal objects are causing the PIM?
Yeah, that can be quite a challenge. I think the way I've seen a lot of people do it is, I showed the pictures of said that if you add attenuation between the antenna and the PIM source, it's going to reduce the PIM. Well, one way of doing that is to get a sheet of RF absorber and physically go to the antenna and move it around and find out, okay, all of a sudden when I blocked this area, all of a sudden the PIM was reduced, and it helps you isolate into the problem.
Okay, great. Earlier, you talked about the 20 dBm limit for antenna power. Is that composite or per band power limit?
I think of that as being a per band power level. So that's the channel power level on a per band basis. Because if we compare back to the testing I'm doing CW testing with individual CW tones at 20 dBm. So it's more as you add more power, obviously for multiple bands, the composite power is going to certainly increase.
Okay. Next question: is it possible to have too much PIM, and if so, how much is too much?
Absolutely, it's possible to have too much PIM. I think the definition of what's, there's the old adage that better is the enemy of good enough, and good enough is if the magnitude of the PIM is below the receiver noise floor, you can't see it. It's still being generated, but if it's not at a level that's rising above the thermal noise floor of the system, then don't worry about it. So it's an interesting and difficult calculation to try to say, how do I get from this CW narrowband test to calculate in my individual band, which has its own particular bandwidth and has its own particular noise floor, what is the level that you need to do? Once again, I refer everyone to the IWPC document. There's at least a paragraph in that section which describes the methodology you would use for determining, based on your receiver, what is the level of PIM that you can tolerate.
Okay, thanks. Can you talk about how a PIM analyzer works a bit, such as does it transmit first and then receive to look the PIM return signal? I guess we have a number of webinars and white papers on the RCR Wireless website that talk about this a little more in depth. But Tom, if you don't mind, can you talk a little briefly about how the PIM analyzer actually works?
Yeah, it's the way the PIM analyzer works is it's transmitting and receiving at the same time, and so we're looking instantly. We're always looking at the receiver while we're doing this transmission of the PIM signals. So to do that, it means that we have to have a very large cavity filter that allows us to be transmitting at 43 or 46 dBm transmit power, and be in the same instrument trying to measure this extremely low magnitude PIM signal. So if you were to open up the box and look at it, you'd see that about 3/4 of the volume is this huge cavity filter for separating the transmit signals we're sending out from the receive signals that are coming back. But because we have that filter system in there, it means that we can be transmitting and receiving at the same time.
Okay, and we have a somewhat follow-up question. If a connector or jumper in the path to an antenna is causing internal PIM, can one just use a spectrum analyzer and a Yagi to pinpoint PIM, or should a complete PIM test be conducted?
Okay, say that one more time. I want to make sure I'm answering that correctly.
Yeah, sure. So if a connector or jumper in the path to antenna is causing internal PIM, can one just use a spectrum analyzer to pinpoint PIM location, or do they need to conduct a complete PIM test?
Well, I guess I'm a little confused by the question, but let's say I have a PIM source that's near one of the antennas, and so you would think that the PIM that's radiating is going to be strongest from that particular antenna. So I guess you could go with a Yagi, and you also need to make sure that you've added good filtering to keep the actual transmit signals that are coming through from desensitizing the receiver. But a Yagi, a good filter, and good dynamic range to be able to isolate in on the frequency of interest yeah, I guess you could do that. But all it's going to tell you is that, okay, the PIM is coming from this antenna. So I guess in theory you could do the same thing if you wanted to for the external PIM sources. If you're walking around the antennas and found the one that was the hottest, that at least gets you in the right ballpark. Is it going to pinpoint it? No. The problem with the Yagi is the beam width is so wide that it'll tell you that it's over there, but it's not going to help you isolate down to within a few feet of where it's located.
Okay, that's great. So is there a way to identify a possible PIM issue remotely? I guess
Yeah, absolutely.
that's it.
Yeah, absolutely. Because there, at the end of the day, PIM is interference, and so anything that causes interference typically is going to be seen as a noise rise in the system. You're getting elevated noise, and that's your first indication that there's a problem. Now, PIM is not the only source of elevated noise, so you have to do another level of investigation to determine, is this increase in RSSI or RTWP, whatever you're using as your measure of wideband power or receive power, is it something that's PIM related? And the most common way I've seen, if you're trying to do this as a remote detection, is to run an algorithm or run a script on your base station that allows you to access either the pilot power or OCNS if it's an LTE system, and generate traffic. So you can generate pilot power traffic, which is going to create energy in the system, and you can set that energy high and you can set that energy low and look at what happens to the RSSI as I'm increasing or decreasing that pilot power. And if you see a correlation, that is, I increase the pilot power, I'm seeing an increase in the noise, that's a good indication that PIM exists. Now, I've seen, I believe companies like Ericsson are offering this as a service, that if you want to sign up with Ericsson and you own Ericsson equipment in your network, they have an algorithm that will do this as a remote test during the night and come back in and tell you these are the sectors that have a high probability of PIM. If you are savvy enough to write the scripts yourself and have access to that, then as an operator you should be able to do that on your own.
Okay. We have time for just a couple more questions here. So as we continue the rollout of fiber that we're seeing these days, can PIM be introduced on a fiber optical cable?
I said no, but as I was saying that, I went back. In fact, in the white paper, I claimed that was not possible. Then I went back and started doing research, and it turns out that they don't call it PIM. I can't remember what the name is, but if you have WDM, which is where you're putting multiple wavelengths together into the same fiber, the dispersion of the fiber can actually cause something that, when you look at it, you go, well, wait a minute, that's PIM. So the answer is there is some documents out there that are describing in tightly spaced wavelength WDM systems a phenomenon that to me looks an awful lot like PIM. But as long as you're using coarse division multiplexing or single wavelengths, then you're not going to see this problem.
Okay, and then how long is an appropriate amount of time to measure for PIM?
Unfortunately, I wish there was a fast answer for that. So let me try to slog through that. PIM is supposed to be a dynamic test, meaning that when you are building out the cable infrastructure, you really should be tapping on each of the connectors. So you have to have it. Your test needs to be physically long enough for someone at both the head end and at the tail end to be physically tapping on the instrument. So, am I going to learn anything different in the first 20 seconds compared to the last minute and a half? I've got data that says no, that if I have a steady state PIM source, I don't see it dramatically changing over time during the test. So it's really, the answer is the test needs to be long enough for you to physically go do the tapping that you need to do. I've done, when I get to the antenna, you no longer are tapping on the antenna in an in-building space because there's no physical, easy way for you not to be part of that measurement. I mean, I guess you could stand 10 feet away with a wooden bat and beat on it. But generally speaking, if you're using high quality antennas, you don't need to do that level of tapping on an in-building system. But in those cases, I find that one of your worst problems is the frequency you're testing at. You're testing at a frequency that is also used by the mobiles to communicate back to the base station. Best practice says choose a IM3 test frequency that's in guard band, so that in theory there's no mobiles transmitting. But if you're sitting there and it's perfectly calm, and all of a sudden I see a 60 dB increase in noise and it goes away, that's probably not PIM. That's probably caused by a mobile actually transmitting while you're trying to perform the test. And so I have seen cases where the test was specified to be conducted at a frequency that was in the middle of the traffic channel. It was done at a time when there were mobiles in the building. The reason that the DAS system was being built was because there was poor coverage, so all the mobiles are increasing their power and trying to transmit. So it made it such that the only way that you could truly determine the PIM of that branch was to set your test duration to 5 seconds and keep going until you finally got a measurement that was done while the mobiles were not transmitting.
All right, that's about all the time we have for today. I want to thank everyone for attending today's webinar, Passive Intermodulation Concerns in In-Building Wireless Systems, presented by Anritsu. As always, I want to thank Tom Bell, Senior Product Manager at Anritsu, for a great webinar. Thank you, Tom.
All right, thanks, Kyle.